Enthalpy of chemical reactions. If a reaction is at constant volume, then V is equal to 0, and no PV work will result. So the internal energy is equal to Q minus PV delta V, and since we just said that work was 0, then the internal energy is equal to QV. The V reminds us that we're at constant volume. At constant volume, the heat change then is equal to the internal energy. If a reaction is at constant pressure, we can then say that the heat is equal to the internal pressure, or internal energy, plus PV. This is also known as enthalpy. So enthalpy is symbolized by H. So delta H equals delta U plus P delta V. So when the reaction is conducted at constant pressure, Q equals enthalpy. Enthalpy of reactions. Since most reactions are at constant pressure, they're open to the atmosphere, heat change is the change in enthalpy. So delta H of the reaction equals delta H of the products minus delta H of the reactants. For endothermic reactions, enthalpy would be positive because our products would have more energy than our reactants. For an exothermic reaction, enthalpy is negative, and so our reactants have more energy than our products. Thermochemical equations show the enthalpy changes as well as the mass relationships. So you always specify the physical states. You can multiply both sides by a factor, and delta H must change by the same factor. And if you reverse an equation, then the sign of delta H, or enthalpy, would change. So if we take a look at some examples. Number 1, calculate the heat evolved when 266 grams of white phosphorus, which is P4, burns in air according to the following equation. So the first thing that we want to do is take our grams of P4 and convert it to moles. And then looking at our balanced equation, we know that 1 mole of phosphorus will give off negative 3,013 kilojoules. And so we get an answer of negative 6,460 kilojoules being released. Number 2, calculate the heat evolved when solid water reacts with carbon dioxide using the following data. So here, this reaction at the bottom is the one that we're trying to get to. If I was to add the top and the bottom together then, or the top and the middle reaction, I should get the bottom. I want CO2 as a reactant. I want 2H2O solid as a reactant, and here it's listed as a product. So I'm going to take my reaction and I'm going to flip it so that water solid yields liquid water, which means I'm going to flip the sign to positive. I also want 2 of those, so I'm going to multiply it all by 2. That means I'm going to multiply my integer by 2. I want CH4 as a product, and it is, and 2O2 as a product, and it's there. So I don't need to change anything about the first enthalpy. And then I simply add them together. And my enthalpy change for this reaction would be 902.42 kilojoules per mole. Comparing enthalpy to internal energy, we can use the equation delta U equals delta H minus RT delta N, where delta N represents the number of moles of gas minus product minus the number of moles of reactant gases. So this is coming from the idea that PV equals nRT. So for example, what is the internal energy for the formation of 1 mole of CO at 1 atm and 25 degrees Celsius? And then it gives us the enthalpy. So delta U would equal delta H minus RT delta N. Well, R, since we're talking about energy, we need to use the value of R with energy in it. So the R value with energy in it is 8.314 joules per mole Kelvin. Now we have an issue. This is in joules, but this value was in kilojoules. So what I'm going to do is convert this to joules. So we have R times T, and that would have to be in Kelvin, times the change in moles of gas. So you take the moles of products of gas, which is 1, minus the moles of gas as a reactant, which is just a half. Well, 1 minus a half equals half. So my N value would be 0.5. So delta U would equal our kelvins would cancel, leaving us with joules per mole. Now that's a rather large number of joules, so it would make more sense for us to have that in kilojoules. So back up at the beginning, if I wanted to convert the R value into kilojoules, I could have done that as opposed to converting it to joules. So calorimetry. A calorimeter is a closed container designed specifically to measure heat changes. Calorimetry, then, is the measurement of heat changes. Specific heat, which is symbolized by S, you might also see it as Cp, is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The heat capacity, which is a capital C, is the amount of heat required to raise the temperature of a given quantity of substance by 1 degree Celsius. Specific heat, then, is an intensive property because it's independent of the amount, but heat capacity is extensive, so it does depend on the amount. So we can actually relate the two by using C equals ms. So Q equals ms, or mCp delta T. Since that is what heat capacity is, we could just substitute in the capital C. Now Q is going to be positive for endothermic reactions and negative for exothermic reactions. If we look at our example, an iron bar has a mass of 869 grams and it cools from 94 degrees Celsius to 5 degrees Celsius. So delta T, final temperature minus initial temperature, would give us negative 89 degrees Celsius as our change in temperature. We want to calculate the heat released in kilojoules by the metal. So Q would equal 869 grams times a negative 89 degrees Celsius times the specific heat of iron. The specific heat of iron would be 0.449 joules per gram Celsius. So Q would equal negative 34726 joules. It wants it in kilojoules, so that would be negative 34.7 kilojoules. A constant volume calorimeter is a bomb calorimeter. It's an isolated system where there is no change in mass or energy. So Q of the system has to equal 0. So that means the heat released by the reaction is equal to the negative heat of the calorimeter. heat of the calorimeter is equal to this heat capacity of the calorimeter times the change in temperature. And this shows a picture of what a bomb calorimeter looks like. We do not have bomb calorimeters at this school. So a quantity of methanol was burned in constant volume bomb calorimeter. The temperature of the water rose by 4.20 degrees Celsius. If the heat capacity of the bomb plus the water was 10.4 kilojoules per Celsius, calculate the molar heat of combustion. In order to calculate the molar heat, which would be joules per mole, I need to know what the joules are. So first I want to solve for Q. Q equals the heat capacity of the calorimeter times the change in the temperature of the water. So I have a heat, or the amount of heat that was changed was 43.68 joules. Now I want to know what the molar heat capacity is for, or molar heat of combustion for methanol. So there's my amount of joules. Now I just need my amount of moles. So 1.922 grams of CH3OH. That's 32 grams for every 1 mole. That gives me 0.06006 moles. So I'm going to take my heat, divide it by my moles, and my molar heat of combustion is 727 joules per mole. Now the temperature of the water rose by 4.20. That means that the reaction was exothermic, which means this amount was actually released, so it would be a negative 727 joules per mole. A constant pressure calorimeter is like the coffee cup calorimeters that we used in the lab. It measures the heat effects of a variety of reactions, including acid-base neutralization, heats of solution, and heats of dilution. Since pressure is constant, Q equals delta H, so Q equals enthalpy. Heat is enthalpy. We still treat it as an isolated system, so we just neglect the small heat capacity of the coffee cup. So 30.14 grams of a stainless steel ball bearing at 117.82 degrees Celsius is placed in a constant pressure calorimeter containing 120 milliliters of water at 18.44 degrees Celsius. If the specific heat of the ball bearing is that, calculate the final temperature of the water. Assume the calorimeter will have the heat capacity of the calorimeter won't matter. So if we can calculate the amount of heat lost by gained by the steel ball bearing, then we can figure out the heat that the water absorbed. So we'll take the mass of the ball bearing times the heat capacity of the ball bearing times the change in temperature. So we would have to say 18.44 minus 117.82. Alright, let me change this for a second. So I know that the heat lost by the ball bearing has to equal the heat gained by the water. So 30.14 grams times 0.474 joules per gram Celsius times the final temperature minus the initial temperature for the ball bearing equals the mass of my water, and since water has a density of 1, it's 120 grams, times the specific heat of water, which is 4.184 joules per gram Celsius, times the change in water. So final minus 18.44 degrees Celsius. Now these two final temperatures have to be the same. So now all you have to do is solve for x. So we have 14.29 times x minus 117.82 degrees Celsius, and that would be joules per Celsius, equals 502.08. So 14.29 minus 502.08. Combine like terms. Oh, that should have had the x there. So x equals a negative 22.4 degrees Celsius. So that would be the final temperature of the water. I'm sorry, that would be the change in the water. So, no, it should be a positive. I'm sorry, positive 22.4 degrees Celsius.